Alright guys, tonight we're going to do a 486 build from start to finish. There's going to be a massive video card evaluation that'll involve both PCI and VESA local bus video cards. And of course, in the end, only one's going to win. We're going to discuss the benchmark tools that will be used to measure success as we walk through this optimization, and there's going to be an enormous amount of data presented. This video is also going to cover the unanticipated but necessary repair procedure of the damaged VESA local bus card slot that was discovered shortly after this board was acquired. I'm going to cover the process of programming a new EEPROM to bring the motherboard to the latest BIOS revision. We're going to discuss the BIOS parameter optimizations that will be chosen to get best system performance, but also guarantee rock-solid stability. We're going to discuss and select more than one local bus speed in this evaluation to understand its effect on CPU performance and video card performance. And in the end, we're very likely going to have an overclocked CPU, which I think will be fun. And I'm going to give new meaning to the word turbo switch by configuring the keyboard lockout switch to allow us to change CPU frequency on the fly. I'm also going to cover the installation of a brand new PowerSpec brand power supply to protect this high value motherboard. Tonight's build is an attempt to reproduce a 486 system that would have been sold in mid to late 1996. At this stage in the market cycle of the 486, major OEMs had moved on to Pentium technology. This type of system was almost exclusively built and sold by smaller distributors, computer shops, or built by individuals sourcing mail order components. Customers seeking this type of machine were extremely budget oriented, or had the goal of upgrading an existing legacy system such as a 386 or early 486. My use case in building this machine is to play early 386 DOS games on up to and including early Windows 95 games. And this machine is for sure going to be able to play DOS IPX network games such as Doom, Hexen, Heretic, Descent, maybe even Descent 2. The main board in this build is exceptional. This is the PCChips M919 version 3.4 BF. This is the final release of the infamous M919 board series. This Socket 3 motherboard supports the full historical range of 486 class CPUs, as well as the 5x86 class quadrupling chips that were offered by AMD and Cyrax. This board incorporates the UMC UM8881 and 8886 chipset. This board is referred to as a VIP board, indicating that it supports both VESA local bus, ISA, and PCI local bus. It has integrated dual IDE channels. It supports 25, 33, 40, and 50 MHz local bus speeds that are jumper selectable. It supports 72-pin both fast page and EDO SIMs. Unlike its earlier predecessors, this board has no fake cache chips. In fact, you can see where the solder pads are empty in the lower left-hand corner. Instead, it incorporates a cache slot similar to a Coast slot, and this board has a 256 kilobyte cache module installed. The CPU we're going to incorporate into this build is the AMD 5x86 P75. This is a clock quadrupling chip that this particular version is rated for 133 MHz and is the Suffix ADW version. Before we move this motherboard and the rest of the hardware into the case, we're going to address several issues while the board's out of the case and on the benchtop. When I initially evaluated this motherboard, I discovered that there was no video output from any VESA local bus video card plugged into this board. As I hunted for the root cause, I discovered that there was a single spring connector in the brown VLB slot that had collapsed. If we look closely at this VLB slot, you can see this is out of place, and then down in the slot you'll notice that there is a empty spot, as though it's collapsed or somehow fallen out of place. So the next step is going to be to replace this slot connector. Here we begin the desoldering process for this VLB slot. I have it securely, I'll say fixtured, so it's not going to move around. I'm going to be using my Hacko FR301 on the number 3 heat setting. So that's a little on the hot side, but I'm going to try to be fast and aggressive and minimize the pressure that the point puts on the PCB. I'm going to apply Kester's 186 solder flux. We'll do the rest in time lapse. Okay, I've done the initial desoldering, so now I'm going to take this and do a wiggle test and watch all of the pins and see how they behave. If I see any that are not moving, that's a sign I might have a via that has not been fully desoldered. If that's the case, I'll resolder it, re-extract it again. You know what, I might have one that I missed. I've got a feeling I might have one right here that didn't go. It's okay. Not going to reuse the slot anyways. Okay, we have a single pin that did not desolder, and it pulled out when oh, actually there it is right there. Okay. I examined this under the microscope, and I don't see any issues with the solder mask or the vias. Everything looks to be in good shape. I don't believe there's any damage from the desoldering process. So the next step is going to be to set this up with a soldering iron, and we're going to go ahead and solder in the harvested VLB connector. I've got the solder station set up for a tip temperature of 370 Celsius, which is about 700 Fahrenheit. And while the lead tin solder I'm using has a significantly lower melting point, this higher temperature compensates for heat losses to the components and allows the solder to flow well. The solder I'm using today is Schneider branded electrical solder. It has a 63% tin, 37% lead composition, and that's known as the eutectic point. That's actually where the melting temperature is minimum for that combination of two metals in one alloy. This melting point is around 183 C or 361 Fahrenheit. This is our harvested VLB slot with good spring connectors and good pins. All right, we've got all pins protruding. And I'll do the rest in time lapse here. I finished the repair of the VLB connector. I made sure to use 91% isopropyl alcohol to rinse all surfaces, both the back of the printed circuit board as well as into the slot itself and beneath the slot. And then I used high pressure compressed air to blow all of the fluid and any other foreign debris out. I made sure especially to look for any signs of lead solder balls or any debris that might be electrically conductive. I've installed two 16 megabyte EDO SIM modules, and I've got the motherboard set to run at 33 megahertz times 4, which is the standard setup for this particular CPU. This will be our first power on test. So I'm going to attach power, a floppy drive, ID hard drive, and one of my PC local bus video cards, and we'll boot it up. We'll run a stress test via a couple of benchmarks, make sure we have good system stability and good video quality. Let's go ahead and run Doom. .3D Bench 1.0C. Chris's 3D benchmark. PC player benchmark. And last but not least, QuakeTime demo. We've completed a trial of all the video benchmarks I'm going to run in this evaluation, and I've seen no issues. No hangups, no crashes, no anomalies. So I think we have a good repair. So next we're going to move in the direction of getting this board ready to do the full-blown benchmark evaluation. But first, I want to take a look at the BIOS. We're paused at the post screen right now, and as we can see, we have an AMI BIOS, and the release date is 5/6 of 1996. So let's take a look at RetroWeb and see what options there are. Here's a list of available BIOS ROMs for this motherboard. The one we have currently installed is the original and the earliest. I'm going to choose the one dated 9/15/1998. For this task, I'm using my XG ECU Pro T48 Universal Programmer. The replacement EEPROM is a Winbon W27C010-70. I've selected the appropriate IC designation in the device menu. Let's go ahead and read it. There is information on this EEPROM, and it was the used one I bought off eBay. Let's go ahead and erase the device. I always do a blank check just to make sure. Very good. Let me read it. All registers are F. Okay. Let's go ahead and load the binary ROM. Let's program it. Let's carefully remove the old EEPROM. We do have a new BIOS date of 9/15 of 1998. This is a fairly typical AMI Win BIOS. Let's walk quick through all the settings. I've got a 1.44 floppy designated. We'll skip to the Auto IDE. This tool works. We have LBA as yes, that's good. Oops. In the advanced menu, this is more my preference. I like to skip the memory count. I like the floppy drive seek Abu. I like the E than C sequence. We obviously have the system boot speed up at high, internal external cache enabled. The video shadow RAM is activated. I have the most aggressive cache speed settings of a 212. I've got 0 wait states on the RAM, DRAM. This is the divisor for the PCI clock to ISA bus ratio. So right now we're at 33 megahertz, and so 33 divided by 3 would be 11 or so, and that's what our ISA bus speed will run at. And unless there's a stability issue, we can leave it there. The options are 2 or 4. And if we eventually go to a 40 megahertz local bus, I may change this to PCI clock divided by 4, because otherwise it might be too fast for the ISA bus. Got the L2 cache as write back. I'm going to leave the video BIOS cacheable disabled. In my experience, I've seen instability arise for a limited gain in performance. And I'll leave everything else the same. For peripherals, nothing really to change here. So let's go ahead and save changes and exit. And we'll go into SpeedSys just to verify nothing has changed adversely. SpeedSys has completed its cycle, and as we can see, we still have our L1 and L2 cache performing. Our CPU index has not changed, so at least at this point there's been no adverse effect of the BIOS change. Now that we have the motherboard repaired, configured, and fully operational, we're going to move on to the massive video card evaluation. This collection of video cards represents a broad survey of cards that would have been available in the 1994 to 1996 timeframe and would have been candidates for a build like this. And this is intentional because it allows us to see the contrast of video card performance, how the chipsets evolved in that time frame, and especially how they perform on objective benchmarks. It helps us sort out whether or not the bottleneck lies in the video card or in the CPU and chipset itself, and under what software conditions. I'm going to briefly introduce 19 PCI video cards and 8 VESA local bus cards. In general, I'll have them grouped by brand, and I'll make a few comments about their release date, the chipset, and in general where in the market they served, and anything else notable about them. In this collection, I'm going to be evaluating 3 separate Trident PCI video cards that represent the time frame from 1994 to 1996. The first card is the TGUI 9440. This card was introduced in 1994 and was marketed mainly towards 2D Windows applications. The second card is the TGUI 9680. That was a significant evolutionary step and was introduced in response to the S3 Trio 64. It also features MPEG-1 video acceleration and 135 MHz RAM DAC. The third card is the ProVidea 9685. It's essentially a 9680 core, but the RAM DAC was upgraded to 170 MHz, and there are versions that have TV out and S-video ports. We're going to be evaluating 2 variants of the Matrox MGA Millennium PCI video card. This card was released in 1995 and is well known for excellent 2D acceleration, early 3D support, and excellent image quality. I have 2 variants of this card. The first is the full retail version with the 6 MB RAM upgrade, bringing the total video card RAM to 8 MB. The second is an OEM compact version with 2 megabytes on board. And I'm curious to see if there's any performance difference, possibly due to different RAM DAC speeds. The next card is the infamous 3DFX Voodoo Rush. This specific variant is the Intergraph Intense 3D Voodoo. This card was introduced in 1997 and really falls outside the scope of this machine build, but I thought it'd be interesting to throw it in and see how it does in our mix testing. This card was 3DFX's attempt at a combination card that has both 2D and 3D acceleration on one board. This 3DFX video card was principally designed to run under a Windows environment with very specific drivers, so I don't expect a lot out of it in this DOS-only environment running the benchmarks we're going to run, but I think it'll be interesting to see how the performance falls apart given the conditions of the testing and being coupled with this relatively slow Socket 3 CPU. We're going to be evaluating 2 Cirrus Logic PCI video cards tonight. The first was a Cirrus Logic 5430. This was released in 1994 and features a 32-bit host interface and was targeted mainly towards desktop applications. The second card is the Cirrus Logic 5446. It was released in 1996 and features a 64-bit host interface. This was a significant improvement for 2D acceleration. I'm going to be evaluating 3 separate ATI PCI video cards. They represent the range from 1996 into 1997. The first card is the ATI 3D Rage 2. This card was a follow-up to the original 3D Rage and was designed to handle basic 2D and 3D acceleration. The second card is the ATI 3D Rage 2 Plus DVD. This card came out in 1997 and was very similar to the ATI Rage 2, except it added MPEG-2 decoding. The third card is the ATI Rage Pro Turbo. This was a significant upgrade and was an attempt to compete in the 3D gaming arena with 3DFX and NVIDIA. This card is the Diamond Stealth 64 2001, based upon the ArcLogic ARK2000 PV chipset. This card was introduced in 1995 to compete directly with the S330 at the time. This card is relatively hard to find, and it'll be interesting to see how it stands up to the S3s in this collection. The next card is the STB Lightspeed PCI. This card is based on the Sang Labs ET4000 chipset. This was introduced in 1994 and was popular compared to the alternatives of the time. This particular card was a Gateway 2000 OEM board and still has the Gateway 2000 date sticker on the backside. Next card is the Diamond Viper SE. This card was introduced in 1994 and is powered by the Ytech Power 9100 processor. This card was billed as a fantastic Windows accelerator, although its DOS gaming performance may fall into question. This card is the SIS 6326, manufactured by Silicon Integrated Systems. It was introduced in June of 1997 and is really newer than the scope of this project, but I thought it would be interesting to put this in the mix and see what the results are. This card was engineered and marketed with low cost prioritized over gaming performance. And it was at a time when the market was evolving into mass production as well as mass interest in 3D gaming. So its parameters are quite compromised. So it'll be interesting to see how this performs with respect to the older cards. Next up is the number 9 branded Imagine 128 Series 2. This is probably one of the most misunderstood cards in my collection and is a great example of how useful and useless a card can be at the same time. This card and its predecessor, the Imagine 128 Series 1, were the first 128-bit accelerators offered on the market for PCs. This video card actually contains 2 graphic processors. The first is for basic DOS and VGA, and that's a Cirrus Logic 5424, and the second processor is the Imagine 128 Series GPU. This GPU is optimized towards high-resolution Windows 95-based gaming and workstation applications. Unfortunately, since the scope of this build is for DOS gaming and DOS benchmark evaluation only, we're only going to experience the Cirrus Logic 5424 side of this card. Last but certainly not least, I'm going to introduce my 3 S3 video cards. First up is the S3 Trio 64V+. This card was released in 1995 and is very similar to its predecessor, the Trio 64. This card lacks any conventional 3D capability and represents S3's emphasis on 2D acceleration and performance. I think it'll be interesting to see how it does in our benchmarks. The next 2 cards are the S3 Verge and Verge DX. These cards were both released in 1996 and represent S3's first mass marketing of a 3D engine. Verge is an acronym that stands for Virtual Reality Graphics Engine. This was S3's solution to integrate 2D and 3D capability into a single chip. Unfortunately, it was not well received by the 3D gaming community in 1996 and 97 due to competition, However, in retrospect, is viewed favorably for its 2D capability by retro gamers. So it'll be interesting to see how these cards do on these benchmarks. Now we begin introducing the VESA local bus cards. We'll start with 3 models of the S3 product line. First up, we have the number 9 branded 9GXE VL. This is based on the S3 928 chipset. This card was introduced in 1993 and is known as one of the first high-performance VESA local bus GUI accelerators using dual-ported VRAM. Second up is the Diamond Stealth 64 S3 Vision 964. This card was released in 1994 and represents the second generation 64-bit GUI accelerator. It supports faster VRAM and higher color depths than its predecessor. And last but not least, we have the Diamond Stealth 64 S3 Vision 968. This model was released in 1995 and represents the S3's continued evolution in high-resolution support and video playback. This particular card has the 2 MB RAM expansion totaling 4 MB of VRAM. Next up is the Diamond Speedstar Pro VL. This card was introduced in 1993 and is based on the Cirrus Logic 5426 chipset. This particular card has 1 MB of RAM and was actually a Gateway 2000 original equipment card. This card was developed as a mid-range solution for high production, high volume consumer PCs that needed good Windows acceleration. Next up is the STB PowerGraph C33. This card was released in 1993 and is based on the Paradise Western Digital WD90C33-ZZ chipset. This particular card has 1 MB of memory and was a Gateway 2000 original equipment card. This card, when it was released, was billed as a high performer for both Windows acceleration and DOS gaming. These days, these cards are relatively hard to find. It'll be interesting to see how it does on the benchmarks. Next up, we have the Trident TGUI 9400. This card was introduced in 1994 and was extremely popular in low to mid-range machines. It's not known to be a strong performer in DOS gaming, but it's known for its broad compatibility both in DOS and Windows. Next up, we have the TGUI 9440. This card was launched in 1995 and was a continuation of the legacy of the TGUI 9400. This card was marketed mainly towards budget-oriented machines. This card should not be underestimated. Most online forums downplay the performance of this card, but in my experience, this card's performance is shocking. And I'll let the data speak for itself. And lastly, we have the ATI Mach 32. This card was released in 1992 and was one of the first high-performing VLB accelerators. This card is built mainly for its Windows acceleration capabilities and decent DOS compatibility. In my experience, however, it has issues with certain benchmarks and does not work above 33 MHz local bus. Now that we have the motherboard repaired and all the video cards introduced, it's time to begin the benchmarking. So tonight I'm going to be using 5 benchmark utilities derived from the DOS benchmark pack made available by Phil's Computer Lab. First up is the Doom Max Details for Faster PC benchmark in the DOS benchmark pack. That's option B. In my opinion, this is probably the single most valuable benchmark to use, at least for 2D gaming performance in terms of aggregate video card and CPU performance for a machine that would have been built in the 1993 through 96 timeframe, and specifically before 3D gaming was important. This is also an excellent benchmark to run if you want to stress test the machine and possibly exploit any instabilities such as L2 cache or video card issues. Next up is the PC Player benchmark in 320 by 240. This is option 5 on the DOS benchmark pack. This benchmark was developed by the German magazine PC Player and was one of the first benchmarks to focus exclusively on 3D video performance. Next up is 3D Bench 1.0C. This is option 2 on the DOS benchmark suite. This is a 3D benchmark developed to evaluate early 3D cards. Because of its reliance on memory bandwidth and pure VGA card throughput, it is a reliable indicator of general DOS 2D and VGA speed. Next up is Quake Time Demo option C. This benchmark is arguably outside the bounds of this particular build, but I felt it would be useful to include because for sure the CPU arrangement is going to bottleneck this game at a certain per second level, and it'll be interesting to see how the video cards fall in behind that. I would expect that many of these cards will run right up to the CPU bottleneck and other cards will fall significantly below. So I think it'll be an interesting sorting tool, at least for video cards under these gaming conditions. And last but not least, we have Chris's 3D benchmark in 640x480. This is a good overall benchmark to test the raw processing power and rendering capability of a video card and CPU combination. Let's briefly discuss the strategy of running this benchmark evaluation from a motherboard parameter standpoint. This motherboard can run 25, 33, 40, and 50 MHz local bus speed. For the purposes of this evaluation, I'm going to choose the middle two speeds, 33 and 40 MHz. 25 is really kind of pointless, and 50 has too many stability issues and may present an actual danger to the CPU itself. I expect both the PCI and the VLB motherboards to run at 33 MHz. I've evaluated the PCI cards at 40 MHz, and as it turns out on this motherboard, there's actually a reduction in the PCI bus speed when you set the jumper to 40 MHz, so I'm going to skip that for the PCI cards and only utilize 40 MHz for the VLB cards. Alright, let's take a look at our first data set. We have in front of us the results from the PCI Video Card evaluation. The way I have this data arranged is each of the benchmark scores is represented by a colored bar. Doom is the blue bar, PC Player is the red, 3D Bench is yellow, Quake is green, and Chris's 3D benchmark is orange. So what I'm trying to achieve and how this data is represented is to allow the user to quickly look at how each of these cards compare to one another on any given benchmark. So say for example how they all compare in Doom from up to down, but also understand how additively these scores sum up and really what gives you the overall best performance for any one given card, and that's how they stack up from left to right. So as this plot would suggest, the CL5446 is the top performer and the Viper SE on the bottom is the worst performer. So let's walk around this data set and point out any trends that are noteworthy or any anomalies that are interesting. The first observation that sticks out pleasantly to me are the Doom scores. Every one of these video cards, with an exception of two, and really it's just the one on the bottom, is at or above 35 frames per second, and that's where the Doom engine maxes out in its frame rate. So what this tells me is that this motherboard and CPU combination can work with a wide range of video cards and give you excellent Doom play results, which for me, that's important. I'm a fan of Doom and the other games they use the same engine, and to me that's a mark of a great foundational system to play well with a wide range of video cards. And here is one other noteworthy trend. If you look at the top four contenders, the Cirrus Logic 5446, the S3 Verge, the S3 Trio 64V Plus, and the Diamond Arc Logic card, they carry relatively heavy Chris 3D benchmark scores from 28.6 to 27.5. If you now look at the 7 cards below it, which contain all of the ATI cards, all the Matrox MGA, as well as the Voodoo Rush and the S3 Verge DX, they seem to have a handicap on the Chris's 3D benchmark. And these are newer cards that all have some degree of early 3D capability. So my hypothesis would be is that this is some sort of a CPU bottleneck going on with this class of CPU in this system. And that's just my hypothesis, and I would invite anyone from the community to explain it better than me. But my guess would be is that these cards might be better suited in a faster machine, probably Pentium class or higher. And as for the cards that perform in the lower third tier of this collection, these are basically cards that either due to their age or due to their optimization towards, let's say, Windows acceleration, just don't perform as well in 2D and 3D gaming. And that's fine because that was their place in the market. Let's take a look at the next set of data. In front of us, we have all of the VESA local bus data, both 33 and 40 megahertz. And let's keep in mind, at the respective bus frequencies of 33 and 40, the CPU is running at 133 and 160. And it is no surprise that the whole S3 family are basically top performers. We can see that the S3928 is at a significant disadvantage on the Chris's 3D benchmark. That's due to its age and not having the same advancements that the Vision series has. What is a shock to me, however, is how well the Trident 9440 VL does. I was not expecting to see this card do this well on this series of testing. Now let's focus our attention on the difference between the 33 and 40 megahertz bus speed. This shows a significant overall improvement for all cards. Now the ATI Mach 32 did drop off as it won't post at 40 megahertz, but as for the rest of the cards, they performed well and stable. And to illustrate the difference in performance that we'd expect to see going from 33 to 40 megahertz, let's look at this chart here. The bottom row simply shows the percentile change between 33 to 40 megahertz, and that's about a 21% change. And so the bars above it are each video card's respective performance increase, which range between 15 and 19%. So this is an expected change, just based on frequency alone. Now let's take a look at all the data aggregated on the screen at the same time. So above, we have the PCI data we looked at earlier, and below we have all of our VLB data. And what is clear are the VLB cards driven at 40 megahertz local bus speed, coupled with 160 megahertz CPU speed, are clear winners. And to be clear, all these trials were done with BIOS settings most aggressive, with fastest DRAM timings and lowest weight states, and the video cards, when jumpers were adjustable for 0 weight state, they were set that way. So a fundamental question that's arisen from this evaluation is, all else equal, is PCI or VLB faster? So for all else equal to actually be true, you have to have the same bus frequency, and you have to have essentially the same implementation of the video card chipset on both the PCI and VLB card. And in this vast collection, I only have one example like that, and that is the Trident 9440 chipset. So if you compare the results of both my PCI and VLB Trident 9440 card ran at 33 megahertz, comparing the aggregate scores, there's about an 18% difference in favor of the VLB card. Now, the people I've talked to and the research I've done, that gap should be closer to 5 or 10%. So it's not clear to me if maybe I have a poor implementation of my PCI card, because there are different companies that integrate these and there are differences in choices they make, RAM DAC speed, whatever. Or is there an issue with my motherboard in terms of its PCI arrangement? In my initial development of the BIOS parameters, I looked under every stone that could be turned to improve the PCI performance. And at some point you just have to say to yourself, it is what it is. So the time has come to make the final choice on which video card to choose for this build. And I've decided to go with the VESA Local Bus S3 Vision 968 4MB. You might ask the question why I made this choice. Two principal reasons. One, this card was up in the top 3, really almost tied for first. And the second reason being, this card is currently on the shelf and not installed in any existing machine. That way I don't have to go back and find a replacement and reconfigure the old machine. It's as simple as that. Alright guys, this is the part we've all been waiting for. This is where the machine build begins. So let me briefly introduce the hardware that's going to be involved. So by now you should already know we're going to be using a PCChips model M919 version 3.4 with a AMD AM5X86 clock quadrupling processor installed. For sound, we're going to be using a Yamaha YMF 719 ISA card. For video, we're going to be using the VESA Local Bus S3 Vision 968 with 4 megabytes of video memory. For networking, we're going to be using a 3COM 3C509B Etherlink 3 with an RJ45 jack. And I've decided to add in to the mix an ISA SCSI card. This is an Adaptec AHA 1520B. These can be very useful if you want to attach a blue SCSI or anything else externally. The case is a mid-1990s mid-size AT tower. It has 3 external 5¼ inch bays. Has a total of 5 internal 3.5 inch bays, 2 of which are accessible. We're also going to be installing a 1.44 megabyte 3.5 inch floppy, a 1.2 megabyte 5¼ inch floppy, a 24-speed IDE CD-ROM, and a classic Western Digital Caviar 32500, which is a 3-platter 2.5 gigabyte drive, which is a perfect match for this vintage of machine. And we're also going to be installing a brand new PowerSpec branded 500-watt ATX power supply with the necessary modifications to be compatible with this board. As much as I'd love to reuse the power supply in this case, when a power supply gets to be 30 years old, you have to put into question the condition and the integrity of the components and the effects of any potential failure on the output and ultimately your expensive motherboard and video card and other components. So I've decided in this build to install a new power supply. In this build, there are going to be 3 fundamental issues that have to be addressed when installing a new modern power supply into this case. Number 1 is adapting the main power leads to the motherboard. Number 2 is adapting the power switch from the front of the case to the new power supply. And in this situation, we have an LED indicator which is powered via 5 volts, and we'll have to find a way to make that arrangement. Let's go ahead and open up this power supply and see what we have. I bought this at Micro Center, but you can get it anywhere online. This is made by PowerSpec, and it's kind of a low end, but with a good reputation, ATX style power supply. What's important to me is that we have adequate amperage on the 5 volt rail, which in this case is 20 amps, and so I'm not too concerned. It includes a wide range of harnesses, which we don't need, most of them. But principally, we have a 24 pin ATX power connector here. And it has 3 of the 4-pin Mullis connectors for the accessories inside the case. And the rest are a collection of more modern connectors, which we'll have to stow away somehow. Now let's discuss how we're going to address adapting the power supply's main power feed to the old motherboard. So we have this 24-pin ATX header on the power supply. And you can buy these anywhere on Amazon or on eBay. This is a ATX to AT adapter. This happens to be a 20-pin version, but if you offset it properly on the 24-pin, this will fit on the power supply. And then this goes to the legacy motherboard. These 2 leads attach to the old style double pole single throw switch that is either on or off, but not momentary. And on the ATX pinout, there's a provision for power on, power off with that type of switch using these pin locations. Next step is to remove the old AT power supply. Let's go ahead and take off the computer's front panel and see how that is arranged. What's great about this case is that a single screw frees up the front fascia, and then there's a spring-loaded keeper down here, so you can swing the front fascia out, and then this detaches. And you're free to work on the back side of the fascia. This is a lot easier than most AT cases from this era. So going through the interior of the fascia here, this is the 110 volt main disconnector. This is a double pole single throw switch with 4 leads. This is the front LED assembly, or the rear side of it. So this is a 1 plus 2 7-segment displays. So you rearrange these jumpers to get different numbers displayed. We have our 3 front LEDs for power, hard drive, sleep. We have a momentary reset switch. We have a 2-state turbo switch, and this is the keyboard lockout switch. The way that this double pole single throw switch works is you have 2 pairs of leads. So the pair on this side are either connected or disconnected depending upon the state of the switch, and then this pair is also connected or disconnected. So really the hot and the neutral are simultaneously disconnected per this switch. So for our use, we only need 1 set of poles. So I'm going to remove really all 4 of these. You can see we have 4 leads here. So I can use either this pair or that pair. And the way it's going to work is our ATX to AT adapter. We have to junction this wire pair across one of those poles. Now, as we can see, these spade connectors are smaller than the pole connectors. So what I'm going to do is actually snip these off and then reattach another pair that have the right size spade adapters. Okay, so I'm going to modify our AT to ATX adapter. I'm going to snip off these 2 undersized spade connectors. And I've got a pair of essentially prefabbed ones with larger ends. I'll strip, twist, tin, and solder everything, and then cover and heat shrink. I'll do that in time lapse. All right, we're back to the case now, so I can put these back inside. We'll extract that later. Here's our two new power leads for our future ATX power supply. I'll attach these to one of the pole pairs. Now that we have this connected, we have to address the issue of powering our LED indicator board. So this particular board is actually powered by a 5-volt tap from the power supply. And in this arrangement, this is crimped directly into one of the Molex connectors on the old power supply we're going to remove. So what I found, this is a tapped in extension. This taps into a ground and 5 volts off of this Molex connector, and this happens to be a Y splitter as well, so that'll be nice to actually have an extra tap inside the case. And so all we really have to do is replace it. So I'm going to pull this out. The 5-volt positive is on the right, and even though this is colored yellow, this is actually attached to the 5 volts on the Molex. I verified that. Plug that in there, and that'll be our new power source. We'll feed that through. Next, we will disconnect the old power supply. Out with the old. Now let's install the new one. We have the new power supply installed, so let's go ahead and do some cable management here. Let's get as many of these unused ones wrapped up. And I'm actually going to reserve the upper drive bay, the upper 5 1/4 inch bay, just to keep these in. I don't have any plans for it. There's going to be a CD-ROM drive, a 5 1/4 inch drive, and then the third one will be extra. So I will just use that for now anyways. Bundle these tight. Use a zip tie for now. And we'll get those out of the way. When I install the drives, I'll negotiate the space at that time. One thing I always do whenever I use a 24-pin and a 20-pin ATX in conjunction is I make absolutely sure that I have it lined up, offset the right way, and oriented the right way. In theory, these pins or these receptacles are keyed so you can't mess it up, but I've seen some that are pretty sloppy tolerance and you can actually force them together. So what I do is I make absolutely sure that it is correct, and then I'll use a paint pen, in this case a purple line, just as a visual key, just to make sure I never get it the wrong way in the future. So now, in theory, we have the case repower supplied, front switch is connected to the command, And we're ready for a motherboard. Let's go ahead and install the motherboard in the case. This board is going to be secured at 5 points. The first 2 are through these brass anchor nuts with metallic fasteners. And the other 3 will be via these 3 nylon standoffs. So what I'm going to do is actually keep these nylon standoffs on the board. I'm going to flip the case upside down and keep it vertical, and then I will actually slide it into the case and let it fall in, and then the hats on these standoffs will actually be behind the slots on the case's rear sheet metal. We have the motherboard securely installed. Let's do a quick function test. I'll install a video card, attach the power supply, let's hook it to a monitor and make sure it posts. Let's power it up and see if it posts. Excellent. We have a good power on self-test. So what we have ahead of ourselves now is to finish up the installation. So I'm going to install the CD drive, floppy drives, hard drive, and their corresponding cables. I'm going to do some cable management to get this in a more proper location. And then we'll hook up the front panel connectors to the motherboard. I'll do that in time lapse. All right, we got it together. Cable management is always a treat on these old 90s era mid towers. There's so little space for how many cables you have. We have all the cards installed. Video, SCSI, sound, network. Got the parallel port, serial port headers attached. Did some creative zip tying to get the wire looms for the power supply stowed in a secure place where they're not going to move around. I've done something on this machine that I've not done in 30 years of PC building. That is, I've attached the keyboard switch to a jumper that can allow you to adjust the local bus speed on the fly. If you look closely, this lead goes to this jumper block here, which contains jumper JP3A. And that jumper, whether it's on or off, will determine if the local bus speed is at 33 or 40 megahertz. So I've routed that to the front keyboard lockout switch, or I should say I've repurposed that switch. I've tested this feature under a number of different conditions, and the system doesn't mind having the local bus speed changed while it's on. In fact, there may even be a pathway to get the PCI local bus speed up to 40 megahertz with the proper timing of the switch during post. But that's outside the scope of this video. Maybe I'll do another one sometime. All right, let's turn it on. I've installed the sound drivers for the Yamaha YMF 719, so let's check out Descent.
Zero, zero, zero.
Let's check out Duke Nukem 3D. We're in the DOS benchmark pack, and I did an F5 on boot to not load all the drivers so we can do a good speed sys and landmark evaluation. So right now the board is set at 133 megahertz CPU speed. Now let's check out landmark system speed test. All right, so we're registering that it says 139, but it's supposed to be 133, and here's our relative speeds. Let me change the scale here a little bit. There we go. Yeah, we'll go ahead and flip the key. Notice we got a boost in the CPU and FPU. The CPU clock in the video doesn't update, so what I can do is step out, step back in, and now it's accurate. Our CPU clock and our video output changed. Let's go into a speed sys here. As you can see, we have our 160 megahertz indicated speed. We have our performance index at 60, which is about what you expect for this condition. And we have our L1 and our L2 cache timings indicated. This has been a fun build for me. I've built computers for many years, and this is the first time I've ever pushed a Socket 3 platform to this extent. I've never overclocked a CPU, really ever, until now. I've never done anything creative as far as routing the local bus speed jumper up to the front panel. So this has been a lot of fun. I hope it was fun for you. And before we end, it wouldn't do justice to this machine without being displayed next to the proper beige CRT monitor and the proper sound. So here we go. This has been a fun build for me. I've built computers for many years, and this is the first time I've ever pushed a Socket 3 platform to this extent. I've never overclocked a CPU, really ever, until now. I've never done anything creative as far as routing the local bus speed jumper up to the front panel. So this has been a lot of fun. I hope it was fun for you. And before we end, it wouldn't do justice to this machine without being displayed next to the proper beige CRT monitor and the proper sound. So here we go.